quantum computing, of course, is derived from properties that we attribute to the quantum world, known from the Schrödinger's equation and other approaches to quantum theory. And the neuromorphic computing strategy we derive, or science derives, from properties of the brain, the so-called spiking networks. This is not so much in contrast to the neural nets, because they also have been derived originally from properties of the brain as models. And this is certainly a very interesting new development to discuss this in context of AI. A second objective is to discuss the possible competition or the complementarities and synergies and the concrete application perspectives of emerging computing technologies and their impact on science and economy. This will be part of what we discuss here. And the third, let's say, objective is to draw conclusions about a possible future emerging computing infrastructure landscape to be built in Europe and beyond. It's very clear that when we try to integrate new technologies, we want to do better than we did before. And at this time, it appears that quantum computing, if quantum computing comes up to be productive, will be integrated in an HPC environment. So I'm happy to welcome the panelists. They are just now equipped with the technology, but in view of the fact that we started the whole session 10 minutes late, let's already start, and I will go through the panelists in sequence, and I will join step by step. So our first speaker in the panel is Professor Harry Bowman. He's a professor in the field of algorithms complexity theory, so this very high mathematically overloaded type of theory, and quantum computing at the University of Amsterdam, a group leader of quantum computing group at the Center for Mathematics and Informatics, and the executive director of QSoft, the Research Center for Quantum Software, which he has co-founded in 2015. He has built the quantum computing group as one of the first groups worldwide and the first in the Netherlands, working on quantum information processing, and he focuses on quantum computing algorithms, complexity theory, showing that quantum computers can not only speed up computation, but that's a specificality also communication. I'm very happy to have you here, and please give us a short statement. As I said before, we want to restrict those statements to about 3 minutes, and then we go on with a question. So please bring up the slide for Professor Bowman. Here we are.
Can we go forward, maybe?
Yes. Sure.
Oh, here. Fantastic. Battery is almost out. Let's see. So, yeah, imagine that we are a few years in the future, and you just bought your very first quantum computer online. And when it arrives in your house, a big black box, well, the first thing, of course, that comes to your mind is, should I have bought it? That's first. And then second, what on earth am I going to do with it? And it turns out that programming a quantum computer is actually not at all so easy. And here's the reason. Because from the very first devices of quantum computing, you see of computing, the abacus up to the supercomputers that we have nowadays, they all use the same fundamental principles. They use bits, and these bits are 0 or 1. And the quantum computer now uses qubits. They're really fundamentally different. They can be 0 and 1 at the same time. And this requires completely different ways of building them, but also completely different ways of programming them. And so now is my thesis. I was asked to put forward a thesis. And that is, we're now in the 1960s, I would say, of quantum computing, where we have a slight idea of what we can do, but still a lot is unexplored. We only know the tip of the iceberg. And until now, there was a lot of focus on building these quantum hardware, these qubits. But I think we should also focus on quantum software now, on what can you do with this quantum computer, so that if it arrives at your doorstep, you know what you can do with it. And second, I think that this is also a very fruitful thing to do for Europe, because that way they can maintain their leading position and become a leader in the quantum software industry. And then maybe 1 second, I also wrote together with some academic partners and industry, because industry is interested, a quantum software manifesto. And if you are interested in endorsing it, then please do so.
Thank you very much. Thank you very much. Yeah, just put it here. So we go on. Dr. Jean-Marc Denis, friend of mine from Athos.
Thanks.
He has been in charge of the Sequana supercomputing technology at Athos Bull, as the HPC International Business Director, and he is a distinguished expert, has been responsible for a lot of the innovations by Bull. He's a strategy expert now for big data at Athos, and in this function, he's at the center of the creation of the digital vision for supercomputing and big data and the implications for organizations and what lies ahead. He has pursued the convergence of HPC and big data technology very heavily. Currently, Jean-Marc Denis is a major driver of the European Processor Initiative with the goal to revive the European processor development competencies. So actually, if you want to know about the architectural path of Europe towards the exascale, he's the right one to ask. Please, Jean-Marc, give your statement.
Okay. Can you hear me? Yeah. I would like to add a few words about what you said. I do agree with you. On 100% of what you said, I do agree. For one point, quantum computing is just at its very beginning in terms of a global new paradigm for information technology science, well, information technology industry as a whole. So we see so many initiatives in hardware, in the US, in China, in Japan, in Europe, that we just don't know how it's going to lead to a concrete general purpose quantum computer, and how long it's going to take, and which technology will support that. Is it the one from annihilers? Is it the one from topological whatever? Well, we just don't know. So the very main focus should be and has to be on software, simply because of the latency to create. If you consider the current situation of IT, it's been based on 2 gates, well, on 4 gates on 2 bits, so on 2 states, 0 and 1. Quantum is whatever number of states, and it's about 13 or 17 different, let's say, gates, if we want to make some comparison. So what can we invent with that? We just don't know. We just know that if we don't start now to reinvent new classes of algorithms or to adapt the algorithms to the quantum world, so the software aspect, we will fail big time, because the hardware will be ready in 10, 15, 20 years, but the software wouldn't be ready. So starting now on software to be ready in 15 years or 10 years, this is the way to go. So from this aspect, I'm sorry to talk for Ethos at this point of time, but Ethos is following this trend. We have developed a full quantum simulator up to 42 stable qubits with a level of noise, untangled qubits, obviously, with a level of noise you can parameter, in order the scientist can start developing on this simulator, and when they want to use some real hardware, they can go to IBM, they can go to Google, they can go to wherever. And the big advantage is this is extremely cost effective. This is in your lab, under your control, where you protect your research and innovation instead of going to a cloud somewhere in the world where someone else can catch up your innovation. So from this aspect, we are extremely well aligned in Europe that the very main focus at this very precise moment of time should be on software. But in parallel, obviously, on the long term, there are many initiatives on hardware side in Europe. Innsbruck is one of the leading laboratories in the world for untangled stable qubits. And there are other initiatives in Germany, which are the largest number of quantum laboratories in the world. In France, in the Netherlands, just to mention a few countries. I don't want to mention the 27 countries, so please don't get me wrong. There are initiatives everywhere in Europe. But hardware will take a lot of time. Software takes much more time. So starting now is the way to go. So to adjust a
Thank you so much.
Yeah.
Thank you so much. Later you can ask your mutual questions, and then we will have fun here in the room. So next speaker is Professor Christel Michielsen. She is group leader of the research group on quantum information processing at the Jülich Supercomputing Center. and she's also professor for quantum information processing at the University of Aachen in Germany. She has worked on simulation of strongly correlated electron systems, and she has created a package for classical fields in electrodynamics, as well as on the foundations, on the very foundations of quantum mechanics. What is quantum mechanics in its essence? And she has a lot of research interests. I would only mention one. She holds the world record on the simulation, on the, let's say, exact as possible simulation of qubits on supercomputers. Currently, I think with 48 qubits. Yeah? This means if you have an ideal algorithm, you can run it up to 48 qubits. Of course, if you want to embed physical elements in that, it is less, but this is at this time the world record of simulation of quantum qubits on supercomputers. Crystal, please, it's your turn.
So I have one slide prepared, and my statement is that linking high-performance computers and various quantum computers might become common practice in the supercomputer centers. And this for two reasons. So on the one hand, one has the HPC simulation of quantum computers and quantum annealers, which can provide you insight in how these devices work, but they also allow you to benchmark them, and they even contribute into their design, or the improvement of the design of these new computing technologies. On the other hand, one can perform hybrid simulations. These are performed on the quantum computer and together with simulations on the high-performance computer. And this creates new opportunities for challenging computational problems in science and industry. So therefore, I think that quantum computers and high-performance computers will go hand in hand, and one will see them more and more in the traditional computer centers.
Crystal, thank you for this thesis to be discussed later in the panel. Now we come to Dr. Heike Riel from IBM. She's one very impressive figure within IBM fellow, serves as executive director of the IBM Research Frontiers Institute, as well as a director of the IoT Technology and Solution at IBM. She's responsible for very much in IBM, for a broad portfolio of research activities, spanning the physical and mathematical sciences, building cognitive IoT solutions, Internet of Things solutions. And we see that you developed tomorrow's architectures, and we would hope that we get some insight today in tomorrow's technologies. Please, Heike.
Thank you very much for the very kind introduction. And yeah, let me give you a few minutes of what I believe is very important. And I would like to start with a few key observations of the current technology, which we all know is kind of coming to a limit. The power-performance trade-off from a device person's view is a big challenge. The data is dramatically increasing, but this also leads to new growing demand of emerging workloads, like in the area of artificial intelligence, machine learning, and deep learning. We will go from functional scaling, from dimensional scaling to functional scaling. And so we are increasingly depending in order to improve the performance of computers on accelerators. So kind of the history we all know from using a transistor and using it for everything we know in compute is kind of gone or is going to an end. So we need to push and more work on driving accelerators for various application formats. And these accelerators, of course, need also the bandwidths in between, right? You need to make sure that you can access accelerators without latency, et cetera, et cetera. So there are a lot of technological components which have to be developed. So if we, just to make it brief, the three main components which we see are the next generation of systems, so continuing the current systems, continuing the scaling as far as possible, going to 3D and hybrid devices. And of course here the Power 9 is one of our workhorses, and in particular the open power. Then for acceleration of the AI workloads, we are working on neuromorphic and cognitive computing. And here we developed a roadmap which starts from using conventional transistors and using them in new architectures, but also going from kind of the algorithm down to what architecture do you need for it and what type of device functionality do you need for it, and in the end, what type of new device you have to build for it in order to get efficiencies and improvements in speed and efficiency of about more than 10,000 for AI applications. And then what has been already mentioned by the colleagues, I fully agree, quantum computing is one of the horses which is coming in the future. It's emerging right now. At IBM, we have been working on quantum computing since more than 30 years. And it's now coming to a turning point where we really can see valuable applications for research and development, but also for the business needs in the coming future. So we were the first who brought the quantum computing on the cloud in 2016. It was a small quantum computer with only 5 qubits, but it has evolved from there to 16, which are now available to everyone on the cloud, so you can use it and play around with it. We have 20 for commercial applications, and we are working on the 50, which is already built, and we are testing it right now. So this will allow new applications, new problems to be solved, which we will never be able to solve with classical computers. And we have to make it possible that all these type of versions of computers can work together in the efficient way. So we have started on a kind of hybrid variation of quantum eigensolver, which uses a supercomputer and also a quantum computer in order to solve problems which can't be solved today. It was mentioned that quantum simulations is very important, and also simulations. So quantum simulations, of course, because this allows us to have the experiment and the hardware and test everything in parallel, and also learn about the errors which are still currently there, which we have to work on, understand, and kind of get rid of in the future. And the software also has to start, and therefore we are also developing a full stack from the individual device up to the compiler and the software. So with this, I'm happy to the further discussion.
Thanks, Heike. Great. So let's go to the fifth panelist. This is Professor Ilyan Todorov from the Dathbury Labs at the Hartree Center. He is worldwide known for the development of the DL poly molecular dynamics code. I remember some time ago you have been with your group at the Jülich Supercomputing Center boosting the code up to full scalability on 550,000 cores, which was seen as quite impossible to do, but you achieved that. So a real expert in how we can go forward in the future of exascale type of codes. I'm very happy for your statement, please.
Okay, my expertise is a little bit orthogonal to the people here, and I'm not so much into quantum computing. If we can move to the next slide. I'm really honored to be invited to be a member of the panel, and just want to reiterate some of the future technologies that are starting to influence us already. So one of the important ones that many of you have already seen and used are things like marketplaces like eBay and Amazon, other ones related to artificial intelligence and robotics, medicinal robots that now substitute nurses in hospitals in the Western world, augmented reality, blockchains for security that can also be involved in the commerce industry, drones. I'm sure members of your family have flown drones already. It's something quite popular with young children. Internet of Things, on-demand supply is something that is very, very popular with big companies. And in all these things, including 3D printing and so on, supercomputing plays a major role, firstly by creating the algorithms, which are the bleeding edge for the supercomputers, and then when chips evolve and small computers can be fitted in devices, these enter these technologies. So I come from this triangle here, I apologize, where I'm a very traditional scientist and software engineer who tries to combine theory with experiments and design computer algorithms. And this is how we have functioned in high-performance computing for decades. And of course, everything to obtain a solution is creating algorithms in specific software to answer scientific questions. I guess in the late 90s and early 2000s, high-throughput computing and sort of the precursor of big data, which we call data curation, started up. And nowadays we have mixed all this in computation with a question and some sort of data analytics or big data, where everything depends on the context. And I'm sure all of you use search engines like Google, and you appreciate that you can find solutions on some simple sentence. But when we look for materials properties, or you want to design something new with new properties, then we have to resort quite often to that triangle here, where we need really hardcore big-scale computers and software that can utilize those computers when they go from homogeneous to heterogeneous architectures. So the most topical bit of my talk is this one, where I spent most of my career and how I see the future of how we have to adapt the software. The very first comments between us at the panel was about the importance of software and algorithms. This is the weakest link. I'm not going to refer to some Soviet Union leader in the past who mentioned that the weakest link is the human, and how we preserve the software that the human creates and ensure succession, because even though software doesn't die, the actual knowledge of the overall infrastructure of the software and how it works actually usually dies with the person, even though the software still works. So essentially, praise has been a very useful exercise where we have looked at various prototypes of how algorithms can be adjusted with respect to components varying on a computer, like CPU cores, accelerators, memory, the type of interconnect fabric, and so on. And our task is to provide extreme scalability, and I'm sure that traditional computing won't get us where we want to get, and quantum computing is the next stage. But I guess what we're doing nowadays is we are having HPC modeling driven by big data instead of actually generating ab initio. We can use experimental data that feeds into the codes to generate our simulations further. And as the machines are not ever big enough for big and challenging problems, we realize we cannot capture all the data. And one of the problems is that, or at least we can solve it, is we have a particular question is to calculate on the fly. We'll lose all the data, but we'll get the answer we're after. So we have to be smart about how we're asking as well. And if we can capture all the data, something that HPC and the e-science haven't quite resolved quite yet in materials modeling is, can we actually decorate that with metadata? Experiments have done it already, but not all modeling software have done it. Because when we decorate with metadata, then we can do data analytics on that data. And one of the problems of big data and then data analytics is that despite all the papers and all the data provided in papers, this data is not clean, and it's very difficult to track it because we don't know how it's been obtained, at what conditions, and so on. And the most important part is when we have all this decorated and working together, is to have a marketplace for modeling and applications. This is what we want, is really, and we're going forward, is to having an Amazon for material science, for example, or for pharmaceutical science. And I guess that is the kind of areas I'm interested in, and what I think are most challenging for HPC scientific and industrial applications. The consumer chemistry is by far the biggest one in the chemistry area where I come from, but I guess Internet of Things and weather prediction, ocean transport are quite popular. And thank you very much.
Thank you so much, Ilian. I'm extremely happy about these, let's say, clear statements on the question of metadata, decoration of metadata. I believe that the communities have to create knowledge bases, and the material science community is certainly one of those. The other one that we will hear in the afternoon is the Human Brain Project, and I guess we get some insight there. Yeah, let me start by asking some questions myself to you, and I would like to start with you, Jean-Marc, as you evaded my original view. You should say something to exascale, and you said more to quantum computing, but this was, of course, fine and very good in the context. But let me get you more as a technical evangelist. I see you at Atos Bühl. You are one of the leading IT companies, and you are, in some sense, Europe's hope for an own exascale technology. You have a deep insight ranging from processors to entire architectures. This also, of course, includes non-conventional acceleration, as you have demonstrated clearly. And when do you expect Europe to become technologically autonomous in the field of supercomputing? I know what it means, and it's quite a difficult notion. One has to define it properly, certainly. Approaching the exascale, in which role do the new technologies, in your opinion, play in the close future? So when we look for, let's say, 2023, 2024, in this quest for Atos.
Yeah. This is a very good question, Thomas, and I think that if we want to elaborate in the details, that we need maybe the rest of the day. So let's try to make it very, very short. So when we talk about autonomy, this is a question with multiple aspects. Autonomy means sovereignty, and sovereignty for many people is military sovereignty. But this is not the point here. Here, the point about autonomy or sovereignty is, at the end of the day, the creation of science, the creation of value for European science and for European industry, and the creation of value as a whole for the European Union, for making the European economy stronger face to the US, face to China, in the worldwide, let's say, economical war. I'm using here a strong word. So beyond the question of sovereignty in high-performance computing or in high-end computing, there is the whole question of sovereignty for the economy, for the creation of employment, and the wellness of Europe as a continent. So this is a very important question. So now, if we are back to the question of exascale computing and sovereignty or autonomy toward exascale computing, I consider there are 6 points of discussion here. The first one is about, let's say, the compute engines, whatever it means, general purpose, compute engines. That could be, so you also have accelerators like GPU. You also have specialized devices like neuromorphic, like future quantum stuff. So all the different class of compute elements that we need to fuel the machine to some extent, to make it work. Then the second point to consider is the interconnect as a whole. So on this point, there is a partial sovereignty in Europe. You've got some initiative at hardware level in interconnect with Extol in Germany, with Ethos and CA in France toward a co-design approach around an exascale class interconnect. There is a question beyond that, the third point, which is the machine itself, the infrastructure, the overall architecture of that class of big machines. So in Europe, we already have sovereignty on this aspect. This is very positive. Then there are the 3 other different classes of sovereignty to consider. This is first the integration, the software stack, the middleware. What's happening between the hardware and the user. So all that class of software, which is very complex, is something that is well understood and well developed in Europe, in Germany, in France, in UK, and in the other European countries, or at Barcelona, they have a great experience and expertise on this point as well. There is a strong know-how in Europe for running very high-end systems, including the upcoming exascale machines. The 5th point to consider is the capacity of creating the architecture and the integration of the all components together. So how to make the connections between the different hardware components and software. On these aspects, Europe is very strong. We have a strong leadership in integrating different technologies. On the very last point, which is the one of most of the people in this room, this is the application ecosystem. You have shown, Thomas, in your presentation around praise, that Europe has nothing to prove in this area in terms of autonomy at the worldwide level. We are amongst the best. There is no discussion on this point. So if we are coming back to your question, the big point, the big hole in the European portfolio as a whole toward exascale is the compute part, the compute engine. So from this aspect, I want to mention only one very important and strategic initiative coming from the Commission that has been initiated very long ago, 10 years ago maybe, with the creation of a European microprocessor industry covering the high-end part of microprocessors that whose intent to fuel the European exascale machines that will come by 2022, 2023 with the Euro HPC consortium between the Commission and today 13 countries. So this initiative is strategic for Europe, for you guys in the room, because that processor will be co-designed between the European scientific community and the industry. And it does answer one of the questions that was asked earlier this morning, which is, well, what do we gain for a European microprocessor? You gain this, gentlemen, because you will have your contribution, your request in this processor. That is extremely important. And beyond that, there will be the consequence for the overall industry with a downscaled version of that very high-end microprocessors for edge computing. And the very first of all will be autonomous cars by 2025 and beyond, where the European industry is very strong now, but that could be killed if there is no control on the technology.
What you have sketched is a very important point, but I still think we have to be careful that we would go for too much autonomy in some sense, because worldwide we need synergy, we need also cooperation. Yeah? That's very clear. Our real problem is that, of course, if the pendulum is too strong on the one side, it might go very strongly on the other side. There's a conservation of energy. That's may be a problem. And so one can very much agree. Europe has to do a lot here, but Europe should not also not forget, if Europe is working in this direction, Europe should not only work for the European market, but for the world market. This requires to have a world view. And let me go forward. This is the reason I would like now to address Heike, because IBM is very strongly involved exactly in these three major aspects, and of course also in the exascale race. The classical exascale computing, and of course the others you already mentioned. You are a forerunner in these fields, and of course the question you already have asked, where you see a major focus of the engagement, it's the integration of this technology. But the question here we have, what is the added value that you would give to the European landscape, in the sense I wanted to sketch, yeah? So we have now a very clear statement from a European company, and the European view must be to emancipate Europe. It's very clear, because if we go on like this, what we have, we will fall back and all our applications on the long run will suffer. But IBM is also working in Europe and with research institutes and with development, let's say, plans, if you like. So the question for us is, what will IBM give to Europe in this quest, and how we can, let's say, go together?
Yeah, so thank you very much for the question. And so first I have to say I feel as a European, right? And also we have quite some, although IBM has a headquarter in the US, we have quite a lot of economic activity in Europe. We also have strong research and development activities in Switzerland, in Germany, in Ireland. We have in France also locations. So there is a lot of activity in Europe from IBM, and we feel the people, of course, also as Europeans. So I think Europe, you always have to think, I mean, everyone has to always think about where do you pick the battle, right? Which battle do you want to win? And there are some battles where you have to say, you have to have a different strategy in order to be strong in that battle. And so I think in certain areas, an open forum strengthens every player in the field. And this is in particular in the open processor ecosystem, I think, where Europe has kind of lost a lot of activity in the semiconductor area. And however, where is Europe strong? Europe is strong, as you indicated, in the integration of systems, in the application of those supercomputers and et cetera. So this is where Europe is strong. So therefore, an open system in that area helps a lot everyone, because then you can use the synergies of the different partners. You can innovate on top of what other partners are doing, and you thus strengthen each other. This also leads to an acceleration of the progress, which is kind of needed, and also builds on the strengths of the ecosystem. If you have a strong ecosystem, this can be a big differentiator to other closed systems. So I think that's something which I believe, focusing on the application where Europe is strong, the integration technology, and really building an open ecosystem which is beneficial to all these players can be a big differentiation. And of course, then in the area of quantum computing, there may be other things you pursue, right? But also here, as we said, software development is very important. Also, the more open we make things, the more quicker we are in innovating on top and bringing out new applications where we can win in the market. Because in the end, it's all about creating value in the market, which brings you economic value back to Europe.
Thank you, Heike, for this statement. Openness is a very important keyword here. I think finally the question is the respect of the different, let's say, world players towards each other. And in some sense, Europe has to gain it back, this respect, and in order to be able to be on par and, let's say, finally to play out the full synergy and becoming most open finally. Yeah? Yeah. That's an important point. Let me come back to the future of technology, where we might have hope that it is not computing in a traditional sense, but it will become computing in a new sense, in a way where new fields can be opened. And there are aspects that are very fundamental here that even touch the philosophy of mathematics. And there are, of course, aspects of infrastructures. Let me start with the philosophy of the whole thing, or the basics of the whole idea of quantum computing. And with Professor Bowman, you are looking at these emerging quantum technology through a specific, let's say, view of a complexity theorist. Yeah? That's your mathematical background. And so I think you are one of the few that are able to, let's say, find out or to reveal if those technologies might eventually have what we would see the holy grail, exponential speed up, etc. And of course, then the physical limitations also from a more mathematical basis. How does this, say, originally ideal view? You have the ideal qubits, and you can do things that you might do through algorithmic steps of the Schrödinger equation, yeah? That finally leads to a result you can then read off in a stochastic sense. Yeah? How does this really comply with the realities of physics and of machines and systems that we are utilizing? Are we, in some sense, having a hybrid situation where some people tell us, let's say, fairy tales, or are we really close to what we would call a quantum computer? So there is no, let's say, in the opinion of the everyday physicists even, not a clear opinion on that, because you can read this article and you can read this article. But finally, it is very, very important that we get means and critics to decide between those, let's say, situations. Is it ever be possible to get the promised holy grail, the exponential speed up? And is Europe on the way to become the front runner here?
Thank you for the question. I guess it's sort of, in some sense, the difference between fairy tales and actual true life. And I do think that, I mean, this is science, so these are certainly not fairy tales. And I truly believe, so this is my opinion, that we will have, in the near future, some computation that cannot be done on a classical computer. Whether that's exponential or not, I don't think that's even so important, as long as it is achieving some kind of speed up. And then you talked about the differences between sort of an ideal view of a quantum computer and the real-life implementations thereof. And now I immediately go back to actual classical computing, and I thought, while you were asking the question, I was thinking back to Alan Turing, who is seen as the founding father of the conventional computer. And he wrote a fundamental paper in 1936, and only a mere few years, and it was about an idealist mathematical model of what a computer is, and only a mere few years later, he actually built a very primitive one called the bomb, and he used that to crack the German Enigma code, and that shortened the World War II by a significant amount. And so I think, yes, this ideal model of a computer is necessary and important. And then you will see intermediate noisy models that are not perfect, that are not universal, as we complexity theorists say, but that nevertheless can perform certain tasks, like in Turing's case, he could crack part of the Enigma code, and maybe in this case we can simulate some quantum system, or we can do, God knows, something else. And then on that way, we will build eventually very stable logical qubits, to which these idealized algorithms that we develop will apply, and they will run on them, just like in classical computing is the case. Right? We have idealized algorithms, and they also run on classical computers. And moreover, these noisy intermediate models, you can make them not noisy, or you can make them stable precisely by using, again, idealized ideas of fault-tolerant computation and error correction. So these things go hand in hand. So you will develop the hardware, and hand in hand you will also develop solutions that make this hardware more stable and more feasible. And I think this loop is actually very important on one hand. And on the other, I think it's very important that you also let these idealized algorithms be developed, because we need some more and new applications that eventually can be run on this quantum computer. Sorry.
Thanks a lot for that. I also think that this is the idealized algorithms that finally are the algorithms, and we try to get them really realized in physics, yeah, in the physical world. Yeah, thanks for these statements. I believe we can come to that in the one of the next questions. But before I do that, I would like to address Ilyan again. He's one of the creators of a molecular dynamics package that exactly tries to solve one of the previous intractable problems. 20 years ago, we could not do what we can do now with better algorithms, with better computers. You are deep in this understanding of impact of new technology, certainly by this. I also believe that you have anticipated what you would do with a quantum computer. My question actually is, are we on track in Europe when we concerning, let's say, or concentrating our quest to exascale, our engagement to quantum flagship, and of course, as we have it with the neuromorphic activities in the Human Brain Project, as far as finally the field of applications is concerned, would you say, let me be very provocative, the computers are fast enough? Quantum computers will not concern this field, they will concern a completely different field, and neuromorphic, I don't know what, maybe will be outperformed by, let's say, deep learning AI. So what is your view?
Well, in the field of materials, I guess the neuromorphic and quantum computing are not quite there to help and with solving the problems we have nowadays. But in the quantum computing, there's a huge potential, and we will reap what we sow. And if the European Commission Research and Innovation didn't put the seeds for quantum computing and neuromorphic computing, we won't get the advantages in the years to come. And I guess many people, through their careers, they get influenced in their early careers by what is popular then. If you want to infuse the young people with the novel technologies, we have to have a provision for this. So I think we're on the right track. We have to push in these areas, despite that the outcomes are quite far in the future for all of us. Like with the praise pyramid that you show with the tier 0, this is what this is what the European Union wants to invest into the future of technologies in order to stay competitive and in the game. All the rest can be taken by the actual national centers and public funding by the different states within the union.
Thanks a lot for that. We talked a lot about, let's say, scientific implications. Certainly it's also important to talk about maybe industry and view of industry on this technology. So, Crystal, Professor Michielsen, you are leading the interesting group enabling quantum information processing in Europe. In short, EQUIP. It's a very new foundation triggered by you, and it was originally triggered, as far as I'm also involved, by the interest of industry in quantum computing. And of course now the flagship comes, and the real question is in how far we can, let's say, channelize or really help those requests from industry. What is your view? Which application fields of industry will be the most important? Which specific technologies will be the first to make an impact here? And which role will play the infrastructural aspect? So what is your view on that?
So thank you for the question. So of course there is a lot what people consider hype around quantum computing. And also then this makes a lot of industries interested in quantum computing, but that I do not consider to be the real interest. So industries that have a real interest in quantum computing come from aerospace, automotive industries, financial, also chemical and oil and gas industries. And then as far as applications or their important problems, this is mainly risk mitigation, also optimization, scheduling, and some machine learning also, so then more the quantum machine learning. And yeah, it's important for these industries also to have a connection to the academic world, because in many cases they don't have any background in quantum physics, quantum theory, and this new computing technology is coming around, so they come and ask for collaborations. And then of course also the flagship in that respect is helpful.
I understand. But the question I wanted to conclude the question with which role will play the supercomputer centers. What do we need to do now in order to finally be prepared for these technologies?
So one of these things you already mentioned is setting up this user group. Another thing is the unique user facility, which we are planning to embed in the Jülich Supercomputing Center.
Would you recommend this for any supercomputing center? What would be your recommendation for Europe?
My recommendation for Europe would indeed be that many supercomputer centers start with an initiative to have user groups, user facilities, to give user support, and also education in quantum computing, but in combination with HPC.
Thank you so much. So now we do a sort of experiment. I asked the panelists in advance to prepare questions to their other companion panelists. And so we will see what will happen here. But of course, one point here is these questions must be short and the answers must be also very short. Yeah, so they must hit the point. So, Ilian, maybe you ask the first question to Jean-Marc Denis.
All right. Can you give us any practical examples that demonstrate well the merge between big data and HPC?
Big data. Yeah, that's a very interesting question. I would say that in the meteorological field for climatology, this is a very good example, very concrete, where from the tons of data, well, as long as the data has a weight, we have been able, when we say we in the scientific world, has been able to use those decades of data to combine them all together in hybrid models with data extraction, data filtering, data validity, up to the mathematical models for oceanographic simulation, air simulation, and worldwide models. So it's a concrete example. And by the way, this is also an area where deep learning techniques and artificial intelligence techniques are rising up very quickly. And there is that example in Swiss and Lugano, where they are working a lot on this. And ECMWF is also extremely involved in this as well. So I believe that in this area, climatology and weather forecast will be of maybe the first beneficial of the, let's say, the merge or the hybridization of classical HPC with big data and deep learning techniques.
Thanks a lot for that. The data assimilation aspect, of course, it's very important here. Let me come to Crystal. Crystal, I asked you for a question to Heike. So, what is your question to Heike?
Yeah, so Heike, we know that there is a lot of competition in hardware for the qubit devices. So my question for IBM is IBM also thinking about different qubits than the ones they have now, so maybe different connectivity? And then maybe also a second question for the maybe longer future, is IBM also thinking about really selling a quantum computer, or will they stick to the cloud-based access model?
Okay, so for the first question, I would like to draw a bit of a historic parallel. If we go back to '58, the first integrated circuit was demonstrated with 2 transistors, and this was 1 centimeter in square. So very big. At that moment in time, people would also not have believed what is possible today, like with 10 billions of transistors on a chip today. And also the reliability and stability of the individual transistors. So going back that way, also the technology has changed according to build those, right? These weren't MOSFETs. So, but still people used them and drove the business and made what is possible. So I see this a bit in the same way. So choose the technology which is now the most leading one. And you have to, of course, there are different advantages and disadvantages. So we have to come up with a clear metric. We have made a proposal of the quantum volume that we are able to compare different implementations of qubits and have a real, like an apple-to-apple comparison in order to choose the technology you want to go for. And then, of course, along the way, you may learn, hopefully, because we have to. And then you may be able to make other choices on the way, right? But right now, it's clearly that superconducting qubits are the way to go. I don't want to go into details, but these are the way to go. You had a second question, which now I forgot actually what was about
whether IBM in the longer future.
Oh, whether we. So right now, to start the process, to start the collaboration, the easiest is really to make it available via the cloud. Because right now they really need the engineers, the physicists to run those things. If this changes over time, different decisions may be made.
Yeah, because now it's difficult.
It's difficult to run them, right? You can't have them in your office. I mean, that's not possible right now. But you also hear a parallel. Where is your data on your mobile phone stored? Where is the computation done which you use when you derive data? It's all in the cloud. It's not on your phone.
That's true, yeah. Thank you for this statement. Perfect. Jean-Marc, I asked you to pose your questions to Harry.
Yeah. So, Thomas, as you chair this session, my question will be for you. My question is for you.
For me?
Yeah.
Not for Harry.
That's maybe a complex question because it also addresses everyone.
We share the answer. Okay,
so we see that simulation as a whole is getting more and more complex. There is classical computing, there is GPU, so acceleration, there is big data, there is artificial intelligence, there is quantum computing around the corner. So we see that the future is very complex, very hybrid. How do you see the evolution of hybridization of computing in the perspective of those multiple technologies? How to make them work all together? So it's a global question.
So the question is for me. The answer is for me, he meant. So you have to give the answer, of course.
Oh, I do.
Because I know he knows that I'm interested exactly in this question.
Okay. Yeah, so I do think, I mean, some people think that quantum computers, I hear that a lot, are going to take over all computation and will in the near future, we only will have quantum computers in our houses. And of course, that's not going to be the case at all, because there are certain problems on which quantum computers do not at all outperform classical computers, and it's much better to use a classical machine. And the same is true for certain techniques, right? Certain techniques will run much better on a particular classical computing model, and others will run better on a quantum model. So actually the model that you guys have envisioned in Jülich, I think that's what it will amount to in the end. We will have some cloud where quantum computers are happily performing certain computations and classical computers are performing other computations, and the user actually has no clue which of the two computers have run this computation. Like now on the phone, right, this example, we also don't know where this computation takes place. And so I think in the near future, all these techniques will be merged together, amalgamized together into one big melting pot that computes for us.
Very small question. So from this standpoint, do you think that you as a user, you could beneficiate from a co-design approach with the industry to combine all those technologies to your benefit and to your research, to your specific research area?
Yeah, I think so, because I mean, when you do research in this field, you have to know the differences between these two computing paradigms, and maybe you have to also know more about the hardware. So there you need to have this co-design, and you have to work hand in hand. So absolutely there. But from a user point of view, I don't think they will notice it.
Thank you.
Thanks, Heike.
So I have a question.
You are addressing Ilyan.
To Ilyan. Right. So actually, I want to come back a bit to also funding and structures like that, right? So I am a strong believer in not going out and just saying, oh, we are funding this technology, and then we figure out what's coming out, right? So I'm a strong believer in saying, let's define a problem, a fundamental problem we want to solve in 5 years, and then make this happen with a focused approach. So what would be the fundamental problem you want to solve in 5 years?
Well, I guess what's on my heart for such kind of problems is personalized medicine, because producing medicines, even if we know the pharmaceutically active ingredient, is actually a very difficult process. And despite our sizes, we take the same pills, and this is not correct if we have some hereditary diseases. So it would be very interesting if we can solve the problem of personalized medicines. And of course, with Internet of Things, you can be reminded that you haven't taken your dosage later on. So I think that is a grand challenge problem for the population of Europe that is suffering a disease like diabetes because of the modern lives they lead.
Thanks a lot. That's a good question and a good answer, and fits exactly why we want to build better computers. Thanks a lot. Last one of the mutual ones. This is Bowman to Crystal, and so now I hope that some provocative quantum computing question comes.
No, actually not at all provocating, but I think to the point here, because what I want to ask you is, what do you see the role of the European Union in order to bring this field further? I mean, for example, we have this flagship, but do you see another role? And in particular, I mean, do you think we can have other kinds of support from the European Union, besides, of course, more money, but is there extra support that you can think of? And where do you think we should head, being Europe, to become leading? Which niche should we exploit in this future field?
So these are many questions.
3.
Yes.
Too many questions.
Yeah, in Europe, okay, now we have the flagship. I would say this is a good starting point. It's also the first phase of the flagship. To my taste, it has been focusing maybe too much on hardware, not so much on software applications. And so it would be good that there would be maybe a separate initiative, or in the next phase, that there is also more focus on application and algorithms, software, and so on. Because in the end, we need to use these new compute technologies. So, and then an important point is, of course, education. So Europe can do a lot in education of people, and I think this also needs to be done in collaboration with industry, because also industry will need, in the end, these students.
Clear statements to Europe, what has to be done. Now we have got a lot of theses and aspects, and we have about a little bit more than 5 minutes maybe to get questions from the audience. So I would like the audience to ask questions to the panelists and to hope for good answers. So, where are the questions? Please. Yes. And please state to whom you asked it primarily.
Thank you for the opportunity. My questions to the person that give, I think, the lady in the red dress, that give only one slide, but mentioned hybrid simulation combining exascale with quantum computers. And do you believe that this, in the new 10 years, will become reality? I mean, quantum computers to become reality, to calculate and to be able at least to use as some kind of a hardware, not just software simulators. Thank you.
So thank you for your question. My personal opinion there is maybe if we look at quantum annealers, we don't need to wait that long. If we look at quantum computers, then it will take a little longer. So maybe then we are in this time range of 10 to 20 years.
Okay.
So may I add something?
Please, of course.
So I mean, this approach is currently being studied to be pursued. So we have published one paper in Nature where we used the approximate quantum computer. So not a universal fault tolerant quantum computer, but approximate quantum computer, and kind of mapped a Hamiltonian for H2BR on the the fermionic Hamiltonian on the qubits. We have done this for 2, 4, and 6 qubits right now. And this was that you do one job in the quantum computer for deriving the wave function, and then you do the energy minimization in the classical computer. So these approaches are now starting, and the more qubits you have available in the system, the more you can calculate, and hopefully at a certain point, hit the classical, become better than the classical computer.
So, okay with this answer? More questions?
I have questions to all panelists. I'm Nicolae Tanasov from University Asean Zlatarov, Burgas, Bulgaria. How do you see the future of the digital personalization with new wave of the high computing in the technical aspects and the social aspects, in the connections for computing and skills, for education, for researches, for innovation, for social technical new events?
It's quite ambitious question.
I was just wondering, this could take another 2 days to discuss. I think,
So
right?
just pick out one of those.
So I think, you touched education. I think education is really important, in particular for Europe, for going into the new fields. There's a big need for people to be educated. With the quantum computer, let me pick that example. So first we have to communicate things in the proper way, because we have done not a good job in nanotechnology. So the public got really kind of worried about nanotechnology in a broad sense. So we have to be very specific when we communicate. And for the education, I think our brain was wired very classical, right? Because we experience a classical world. I think now becoming tools available like small quantum computers, where people can see how the quantum world kind of behaves. Even for children, the wiring of the brain may become different, and they think more quantum than we do, right? So they get an intuition for what quantum physics means in the end, where we weren't able because we only experienced the macroscopic world when we grew up. So my vision is that kids could kind of start with that and get an intuition for quantum, and there could be more innovation in the future.
So this means a quantum course in the kindergarten then?
So with the quantum experience, where the quantum computer is available by cloud, actually some kids start to play with it, and they don't see that barrier or have this barrier if only we start as an adult to work with it, right? So they start more playing with it, and I think that makes a big difference.
Thanks. So, two last questions because we have to go to lunch. Where are questions? So you all are hungry, which I can understand after all these exhausting and deep-going discussions today. So let's thank the panel for these very enlightening statements, also the mutual questions and the answers to the questions. Thank you very much. So with this, we close the morning session. I'm not sure if the organizers want to make an announcement at this moment, but on the schedule we have now the lunchtime and we will reconvene. Does anybody know when exactly we will reconvene? At 1:40 we will reconvene here. Please.
Thank you. Thank you so much. So now we have lunch break and all you are invited to go upstairs and to have lunch. Thank you.
Thank you.
Thank you, Tomas. Što nam je? Od kabinka to treba